We usually think about the world in terms of pushes and pulls, right? The actual work it takes to get something done. But physicists, well, they have this incredibly powerful shortcut. It's a way to map the energy of space itself. So today, we're going to take a journey from that familiar idea of work to this much more elegant concept called potential. And it all kicks off with a question like this one. Just imagine you've got an electric charge, and you want to move it, but here's the catch. It's sitting inside an electric field, surrounded by all these invisible forces yanking it around. So how much effort, how much actual work does it take to get it from point A to point B? To answer that, we first have to zoom out a little bit, because the rule that's in charge here, the one that governs these tiny electric charges, it's the exact same rule that governs planets, baseballs, well, pretty much everything in the universe. It all boils down to the connection between work and energy. This right here, this single equation is our starting block. It's the Work-Energy Theorem. And all it's really telling us is that when you do work on an object, whether you're pushing it or pulling it or fighting friction, you are fundamentally changing its total energy. So let's break that down. The work you put in can change an object's energy of motion, that's its kinetic energy, and it can change its stored energy, that's its potential energy. But here's the really crucial part. If there are no outside forces messing with the system, the total amount of energy is locked in. It stays constant. It just swaps outfits, It transforms between kinetic and potential. All right, so we have this universal law. Now, let's take it and apply it to our main event, electricity. How does this whole principle of work and energy actually play out in that weird, invisible world of charges? Well, it turns out to be incredibly direct. The work you have to do to move some little charge Q from point A over to point B is exactly equal to the change in the system's potential energy. It's that simple. You figure out the potential energy at the start, you figure it out at the end, and the difference, that's your answer. And this method scales up beautifully. Doesn't matter if you're just rearranging 3 charges in a triangle or you're trying to pluck 1 charge out of a circle of 8. The process is always the same. Find the initial energy, find the final energy, and the work is just the difference between them. But I'm sure you can see the problem here. As you start adding more and more charges, calculating the energy between every single pair gets really repetitive. It's a grind. It works for sure, but it's not exactly elegant. And if there's one thing physicists are always looking for, it's a smarter, more elegant way to do things. And that brings us to their ultimate shortcut. Instead of thinking about all those interactions between every single charge, what if we could just describe the energy properties of the space itself? This is the brilliant idea behind electric potential. Electric potential, which we measure in volts, is really just the work needed per unit of charge. Now, the absolutely essential thing to get here is that it doesn't depend on the charge you're actually moving. It's a property of the location. Think of it like an energy price tag slapped onto every single point in space. And this is where it gets really powerful. The work done moving a charge between 2 points, and so the difference in potential, is completely independent of the path you take. You could take some wild, loopy journey from point A to point B, or just go in a straight line. Doesn't matter. The energy change is exactly the same. So let's be super clear on the difference, because it's a big one. Potential energy is a property of the whole system of charges all interacting. Electric potential, on the other hand, is a property of a single point in space. One is measured in joules of energy, the other in volts, which is joules per coulomb. A subtle but absolutely vital distinction. Okay, that's enough theory. We've got our shiny new tool. Now let's see what it can actually do and why it makes a physicist's life so much easier. So take a look at this problem. We do 50 joules of work to move a 2 coulomb charge. We know it started at a spot where the potential was negative 10 volts. So what's the potential at its destination? With our new formula, this is just a quick bit of algebra. No wrestling with complex forces or anything, just some simple multiplication and addition. Done. And here's another huge advantage. Electric fields have direction, right? They're vectors, and that makes adding them up a real headache. But potential is just a number. It's a scalar. So to find the total potential at the center of this triangle, you just calculate the potential from each charge and add them up. Simple addition. No angles, no trigonometry, no problem. Now this is a fantastic example. At the very center of this hexagon, you've got 3 positive charges making a positive potential and 3 negative charges making an equal and opposite negative potential. And what happens? They perfectly cancel out. The total potential at the center is 0. But, and this is the kicker, the electric fields from all those charges are all pointing in different directions, and they absolutely do not cancel out. This just shows how potential can give us a different and sometimes much simpler picture of what's going on. All right, time for the ultimate test. What if we have an infinite line of charges, alternating between positive and negative, with each one getting twice as far away as the last one, forever? How in the world could we possibly calculate the total potential from all of them? I mean, really think about that. An infinite sum. This feels like a problem that should just be impossible to solve. How do you add things up forever? Well, the solution isn't in more physics. It's in a powerful mathematical tool, the geometric progression. It's just a special kind of series where each new term is just a constant multiple of the one before it. And here's the magic trick. If that multiple is less than 1, the series converges. It means its infinite sum is actually a nice, finite, calculable number. And here it is, the payoff. When we write out the total potential from that infinite line of charges, we see that exact familiar geometric pattern emerge. By using the formula for the sum of the series, this seemingly impossible, infinite problem just collapses. It folds down into a single, clean, elegant answer. It's incredible. So what this all really means is that electric potential is so much more than just a formula or a shortcut. It's a fundamental shift in perspective. It lets us stop worrying about all the individual forces and start seeing the properties of space itself. It's like we're drawing a topographic map of the hidden energy landscape that surrounds us all the time. Which leaves us with a final thought to chew on. We've just used potential to map the energy of space for electric fields. But what other invisible fields, what other hidden energy landscapes are out there shaping our world right now?